All right, welcome. My name is Ryan Hoger. I'm with Temperature Equipment Corporation. This week's topic is CO2-based demand-controlled ventilation systems. As with most weeks, we are recording this webinar for future viewing. So if you got someone in your office who missed it and wants to see it, just let me know, and I can send you a link where they can watch it. So we'll go ahead and start right now. This topic, demand-controlled ventilation, is actually one of my favorite to talk on, and most of you guys that know me know that I like to talk in general. So that's saying quite a bit. I started doing demand control ventilation systems back in the year 2000. At that point in time, it was not something that was easily permitted through code or easily explained to folks. And all of that has changed in the past 5-6 years, and we'll go through the code requirements and or benefits on the energy side. And it's a much easier discussion to have with folks. In fact, now people come to me and ask for this. Unfortunately, I'm no longer in sales, so I'm not selling them anything like I used to, but at least I can explain the technology to them, and hopefully they can get some energy savings. If you guys have questions as we go, type them in the chat/question box in the bottom right-hand corner of your screen, and I'll look over there periodically every 10 minutes or so and see if we have any questions pending that I can try to answer. All right, so the way we control ventilation in buildings. We try to make buildings as comfortable as possible for people so they're more productive and healthy. And the way we've traditionally looked at that is looking at just temperature, and that's kind of how we've always done things. But as most of you probably know, comfort is more than temperature. It's temperature, it's humidity, it's ventilation, it's radiant temperature, it's clothing level, it's air distribution, it's all these different things in one. And today we're really going to focus on making a building more comfortable via ventilation without sacrificing temperature control. It's kind of our goal. So the way we ventilate buildings today, well, the way we ventilate most buildings is the same way that we've always ventilated buildings. We basically fix the outside air louver to a locked position, and then we leave it there all the time. And then hopefully, at least at nighttime, we shut it. But we don't modulate it. We don't track what's going on and what's needed in the space. We just put it to some very high position, which overventilates the space, and we feel we're pretty safe and we're covered. Here on the screen is showing you our minimum ventilation rates dictated by various codes and or standards over time. And you can see, and we'll skip all the really early stuff, but back in the pre-World War II stuff, it was very high. 30 CFM per person was dictated by several codes. Most locations didn't even have a code, but 30 CFM where there was a code, which is a really high number, and would be very challenging to keep those spaces dehumidified. Most of the building stock we're dealing with these days is post-World War II construction, and as you can see there, everything from the 1930s through 1981 was likely designed around 10 CFM per person, which is a fairly decent rate, but not as high as it is these days. There was a brief time in the 80s that we kind of went to a lower rate, ASHRAE 62 standard, 62.1 specifically, reduced from 10 to 5 CFM per person. That was in direct reaction to the oil embargo and the effort to save more energy after what happened in the 70s there. You can see that 5 CFM per person rate was very short-lived, and it did help contribute to some of the sick building syndrome we had in buildings by underventilating them. So then we kind of on the ASHRAE side flipped over and overcompensated for that and went up to 15 CFM per person. Most of the buildings built in the 90s, which are the ones you're very likely going into right now and repairing and replacing equipment on, those are probably designed around 15 CFM per person. And then for a little while in the late 90s, early 2000s, we were at 20 CFM a person. And now you can see since 2004, we're showing here 17 CFM per person, but that's more like an average. As we'll talk about when we go through the code in a little bit, it's really a per person plus a per square footage number nowadays. So it kind of, for a typical densely occupied office space, it comes out to about 17 CFM per person. So this is what happens in a fixed ventilation system, and the buildings you're looking at are probably designed around 15 or 20 CFM per person, the existing buildings. And so what you would have done is taken the number of people it was designed for. In this case, this little bank was designed for 25 people. 25 times 20 was 500 CFM. And that was fine and great, and it ventilated the space, and we kept everything moving, kept the air changing. Awesome. However, when there was less people there, for this example, 5 people in the space that was designed for 25, we still were bringing in 500 CFM. And then later on at night when this bank teller is closing the thing down by herself, she's still getting the full 500 CFM even though she's the only one there. So in most cases, we're not at design occupancy. So in most cases, at least for periods of time in a building, we are overventilating. If you look at zone-based systems, which we're not going to focus on too much today, but we'll talk about a little bit so everybody knows what's going on there. You got an outside air louver and an air handler as shown up here. Let's see if we can actually, hopefully you guys can all see my mouse on the screen here then. So we got the outside air louver on the outdoor air handler, and this guy's job here is to bring in outside air for all of the zones. But as individual zone dampers start modulating closed because of their space temperature requirements, what's going to happen? Well, they're going to get less total airflow, which means they're also going to get less outside air. So on a zone system, it's really not appropriate, a zone system meaning like a VAV system, it's really not appropriate to fix the outside air louver at a set position. You really have to track what's going on in the zones. There are two methods to doing this. ASHRAE 62.1 allows you to do an equation called equation 6.1 that allows you to mathematically predict based on temperatures which zones may need more airflow and based on which zones you define as critical zones, such as a conference room, and try to get the right air to the right spot. The other way to do it is to actively measure the airflow and measure the air quality in those individual rooms. So that's really what we propose to do with the CO2 system. We're not only going to measure temperature in the spaces, we're actually going to take those temperature sensors off the wall and put on temperature/CO2 sensors so we can measure both the temperature and the ventilation rate in those spaces. So as people move out of their offices and all pile into the conference room, we can track that and say, well, we don't really need to ventilate as much in their offices because they're not there. Instead, let's ventilate all the air over towards the conference room because 15 people are sitting there instead of 0. So by tracking the CO2, we can track the people and hence decide which rooms to send the ventilation air to, reducing the overall outside air intake. So kind of our goal with the CO2 system, with the DCV, is to send the right amount of air to the right place at the right time. We really got to try to track this stuff. All right, so how is this all going to work? The first thing we got to do is understand what is allowed, permitted, and required by some of the various standards and codes. So the main standards involved in this discussion will be ASHRAE 62.1, which is the ventilation standard for acceptable indoor air quality, and ASHRAE 90.1, which is the country's energy standard. Both of these feed into the codes. They feed into the International Mechanical Code and into the International Energy Conservation Code, which all feed into the local codes. So this is kind of, the ASHRAE stuff is kind of the research and power behind all the codes. So one of the things we want to understand is that CO2 levels in a space are just an indicator of how many people are actually there. It's a surrogate for counting the number of people. It has absolutely nothing to do with the actual air quality. CO2 is just one chemical that would be in the space, and it's not even a harmful one. There's plenty of other things in there that could be harmful, like VOCs, viruses, things like that we have to deal with a little bit differently, and we'll talk about that. So CO2, like I just said, is not a contaminant. It is not harmful to you in normal concentrations. You basically would have to suck it out of a can in order to have it hurt your body, right? You'd have to be up at like 20,000, 30,000 parts per million for it to do any harm to you. And that's basically more because you're lacking oxygen intake, not because of the CO2 itself. Typical CO2 levels outside are between 400 and 550 parts per million, maybe 375 and 550, depending on where you're at in the country. Here in the Midwest, and specifically in the Chicago area, we are typically between 450 and 500. That's pretty normal. Some of the samplings I've taken up in Wisconsin have been around that 450 also. As you get to more populated areas where there's more cars and vehicles and people, it tends to be slightly higher. And as you get to more rural areas, it tends to be slightly lower. The other thing to stress is that carbon dioxide, CO2, is not the same as carbon monoxide, CO. I cannot tell you how many sets of plans I've looked at where someone was trying to do the right thing and specify, demand ventilation systems and put CO sensors for a conference room or something like that. That's fine for safety reasons if you want to do that, but it has nothing to do with us controlling the ventilation rate. So CO2 sensors are for tracking people. CO sensors are good for demand ventilation systems for like parking garages and loading docks where we're tracking vehicles, not people. So CO2 is for people, for office spaces, schools, restaurants, etc. Typically, people are exhaling at a pretty high of CO2 rate, 40,000 parts per million. The more active you are, the more you breathe, and hence the more you exhale, hence the more CO2. The less active you are, the less you breathe, obviously. CO2 is kind of like, it's very close in its weight to the actual air. Air, as you probably know, is made of mostly nitrogen, also oxygen, CO2, and several other gases. And the molecular weight of CO2 is very close to the weight of air. So it tends to diffuse fairly quickly and in all directions. So it'll diffuse vertically from floor to ceiling and horizontally from left to right, front to back. It'll spread throughout the room pretty evenly, just like humidity. So it's not like temperature in that we have hot spots and cold spots. CO2 will spread pretty evenly throughout a room. Now, if there's partition walls and doors and all that, that is going to obviously stop the CO2 from moving into those other rooms. But in an open room, it's going to spread evenly. So it doesn't really matter if I measure CO2 on the east wall or the west wall or anything like that. It's going to end up being pretty even, and we'll show you that. So like I said, CO2 production is based on what you're physically doing. This chart here, if you look down on the bottom, it goes from 0 to 5 metabolic units. Metabolic units, or met rate, is an activity level measurement of how active a human being is. And vertically, you see up here, we're going vertical with the breathing rate / oxygen consumption / CO2 production. The more I breathe, the more oxygen I consume, and the more CO2 I exhale. So that's all kind of linked together. So metabolic rate versus CO2 production. So if you look on here at, say, office work, it looks like it's about maybe a 1.1 metabolic unit rate, and we're producing CO2 at a rate of maybe, I don't know, 0.3 liters per minute. If you look at sleeping, it's just slightly less than that. So basically, if you're sleeping at work, it's totally acceptable. You're not hurting the HVAC system at all. If you're doing something more active like walking, or say at a gym and you're running on the treadmill, you're probably exhaling 4 or 5 times that amount, because your metabolic rate is 4 or 5 times that amount. So as we set up CO2 set points and things like that, it does get dependent upon the kind of space we're talking about. Offices are going to be different than gymnasiums and things like that. Jeff asks, what about CO2 equalizing from floor to ceiling? The answer to that is yes, Jeff. It does equalize. Now, obviously, if you're in a tall space with 30-foot ceilings and everybody's down at the 5-foot level breathing, there's going to be more CO2 there than there is at the ceiling. But all the CO2 that's exhaled into the room is going to disperse itself evenly throughout the room, vertically as well as horizontally. Each CO2 molecule wants to get equally far apart from the next CO2 molecule. So they're trying to basically symmetrically position themselves throughout the room, as do most gases. Most gases that are the same weight as air, which CO2 is approximately the same weight. So yes, it's going to go vertically as well, Jeff. It does take a little while for CO2 rates in a space to stabilize. The pace at which they stabilize is directly dependent on how much ventilation air I'm bringing into the space. When I say stabilize, that means 20 people come into a room and they stop and no new people are coming or going. How many minutes is it going to take for us to basically get an even CO2 level in that room and stabilize out? So for example, if I am following a code somewhere that has a ventilation rate of 15 CFM per person, I look at this yellow line, I would say in about 35, 40 minutes maybe, I'm going to end up with a pretty stable CO2 reading. However, if I'm only ventilating at 5 CFM per person, it's probably going to take me 2.5 hours to stabilize the reading. Now that doesn't mean that my ventilation system waits an hour, 2 hours, or whatever to start reacting. That's how long it's going to take to stabilize the CO2 reading. It doesn't mean I have to wait that long to start reacting. I will start seeing the CO2 sensor reading start going upward as more people come into the room within a few minutes, say 10 minutes or so. So I can start reacting with my damper then, but I don't have to wait for it to become stable. So we'll kind of show that sequence as we start talking more here. Well, anybody has any more questions, just like Jeff, if you could type them in the question box, and I'll try to answer them as we go. So let's take a little bit to explain why CO2 is in the codes and which codes it's in and that kind of thing. So I'm not going to bore you guys with all the math because I don't think most people on this call are mathematicians. But this is the math that is straight out of the ASHRAE 62. It's been in ASHRAE 62.1 Appendix D for 20-some years. And in reality, the CO2 exhaling rate of human beings, it is what is used to set up the tables for the ventilation rates that are required by the VRP procedure. So it's not that ASHRAE just randomly made up all of these numbers and said, oh, you got to bring in, whatever, 10 CFM per person in a school and 12 CFM per person in a daycare and 5 CFM per person here and there. Those numbers were not made up. They were backwards calculated from the stabilization rate of CO2 generated per person versus what I have in the outdoors. So all this math, and you have it on here as a kind of a reference. I'm not going to kill you with it, but all this math basically boils down to what's the difference in my CO2 rate inside the space and my CO2 rate outside the space. That's really going to determine how much ventilation air I have to bring in or how much I am bringing in. So we can use these equations dynamically, in a building, not just to design a standard like ASHRAE 62 or a code. We can use them dynamically to actually control the space. So when we start doing that, our little bank example with the bank teller lady, 25 people, they were going to have to bring 500 CFM per person. When there's only 5 people there, they can bring in 100. When there's only 1, they can bring in 20 CFM per person. Now, in reality, we're going to have to talk about a few more things because I'm not just ventilating a space only for the people. There are other things in the space like cleaning chemicals and carpet off-gassing I got to think about. And I also have to think about pressurization. If I only brought 20 CFM into a bank, but I have my bathroom exhaust fans running at, 150 CFM, my space is going to be negatively pressurized, and I'm not going to want that. So there's going to be some things that dictate an absolute minimum. So instead of ventilating the full code maximum, I'm going to ventilate something consistently. It's going to be the larger of the per people rate, the building off-gassing rate, or the exhaust ventilation that I have to do for makeup air. And we'll talk about how to calculate those. But kind of in concept, when she's there by herself, 20 CFM per person or something close to that. In the zoning systems, same kind of thing. If I start tracking where the people are moving in the building as they go from their offices into conference rooms or into the lunchroom or whatever, I can track them and I can ventilate to the room that they're in and stop ventilating or minimize the ventilation in the rooms that they're not in. All right, so what does it take to do one of these systems? On some equipment, it's extremely easy, such as a packaged rooftop unit. Packaged rooftop units, in almost all cases, have an economizer on them. New ones certainly do, because economizers are required by code in most states down to 5 tons. In some states like Illinois, down to 2 3/4 tons. So usually you got economizers on stuff that's been put in the past 5-6 years. But even before that, older equipment on larger units probably had an economizer for energy reasons. So if you have an economizer and it's a relatively new economizer, the past 10, 12, 15 years, chances are it has a CO2 sensor input on it. It may be labeled IEQ, not CO2, but it does the same thing. So you can oftentimes retrofit a CO2 sensor onto an existing rooftop economizer and not have to do any work to the economizer or the unit itself. If it has a really old economizer, then either you should look at replacing the rooftop because it's a 20-year-old rooftop, or you might have to change the economizer controls. Or if they didn't have an economizer, you might have to add one. On a zoning system, it's a little bit more complex because I don't just care about one CO2 sensor and one outside air damper. I care about many CO2 sensors from many rooms that are controlling local dampers at the VAV box level, and those dampers are all coordinating to dictate what the main air handler has to do. So really, to do CO2 sensors on a zone system, I have to have a building automation system. I have to have DCV-based controls so they can communicate to each other, share information, and calculate who the worst case guy is. So if I have, say, a 20-zone VAV system, I'm going to end up with 20 CO2 sensors on the wall right next to the temperature sensors, or even better, in the same plastic enclosure as the temperature sensor, wired back to their local VAV boxes that are controlling those dampers, and then we're going to look at those 20 VAV boxes and say, are any of you guys not meeting your CO2 set point, and who's the worst one? Okay, the worst one, you get to dictate the outside air ventilation rate at the air handler. A couple questions came in. I'll try to answer those right now if we can read them quick here. How often are these types of systems used in healthcare, specifically patient rooms? Comes in from Daniel. I have never done it on a patient room, Daniel. We've done it in like lobby areas of healthcare facilities, but I'll show you a chart in a little bit of places that we frequently do CO2 versus ones that we never do it, versus ones that we might do it. Let's see, one more question here and then we'll continue on. Andy writes in, could you speak a little bit about the interpretation of ventilation zones in 62.1, i.e. CO2 sensors and return air ducts can be good representation of the number of people in a wing, like a VAV system for a wing of rooms, similar offices. All right, so in regards to the return air sensors, some codes are now prohibiting CO2 sensors to be used in the return ducts. Some of the utility rebate programs are now prohibiting that as well. CO2 sensor in a return duct is not very useful. It'd be like having a 20-zone VAV system and saying, you know what, we don't need a temperature sensor for every VAV box. Let's just shove one temperature sensor in the return duct and everyone will be happy. So for CO2 sensors, it's the same thing. Putting it in the return duct is not a very good representation of what's going on. If you look back at this little picture here on the screen, if I were to stick a CO2 sensor in the return duct and I had 20 employees in here and they were moving from their offices to the conference room, etc., I would always be reading the same CO2 level from those people. But the damper for their zone would not be doing the same thing. So really I need to know which room the person is in so I know where to send the ventilation air. The only way for me to know which room they're in is to actually put the sensor on the wall, not in the return duct. So for zone systems, CO2 sensors in the return duct is not useful whatsoever. For constant volume systems, it can be used, assuming that it's a big open area and there's no partition walls. Once you got partition walls, those are actually separate zones, even though they don't have a damper, and the CO2 is not going to move between them very easily. The only place that I recommend using return air CO2 sensors is going to be like in a school gymnasium. That's because it's one big open room. You know, it doesn't matter if the kids are in the East Gym or the West Gym, all that air volume is basically the same. And if I put it on the wall, someone's going to mess with it and knock it down anyway, so I might as well put it in the return duct. But I definitely would not use it on zone dampered systems, and I would not use it on constant volume systems with partition walls. So hopefully that answers Andy's question, at least in part there. I'm going to try to play a quick little short 1-minute video. I'm not sure if it's going to push through the webinar screen very well, but I'm going to give it a try and let's see how it goes. All right, so this video here, if you guys can see it, let me know and type in. There's an outside air handler on here and a 2-zone system, 2 damper zones. There's a CO2 sensor on the wall. As people come into this room and start breathing, the CO2 sensor recognizes that. It tells the VAV box, hey, bring in more outside air. It looks like most people are saying the video is not pushing through, so I'm not going to show this example any further because it won't do you any good. I'll just describe what it was going to show. So as one VAV box, as when people come into that particular room, here's what we'll do. I'll just do it with my mouse on this screen. So let's say everybody comes into this conference room right here in the middle. Everyone piles in right there. Right, so everybody just piled into that conference room. As they pile into that room, they're breathing. That breathing is recognized by the CO2 sensor, and that CO2 sensor tells that particular zone damper right there in the ceiling to open up more and to allow some more fresh air in. At this point in time, I still have done nothing with my outside air damper. He's still fixed. I'm just opening up my zone damper more and getting any more fresh air I can out of the existing duct system. And as he's opening, chances are these other zones might be shutting. They might not be, depending on who's still in those rooms. If this CO2 sensor cannot meet its set point by opening up his local zone damper, then what he'll do is he'll tell that damper, hey, I'm not getting it done. And then he'll tell the main air handler, hey, somebody's not getting all the air they need. Then that damper is going to have to go open to a higher fraction of outside air. So we're always looking at all these dampers, in this case 1, 2, 3, 4, 5, 6, 7, 8 dampers, and saying, hey, which of you guys is the worst one? The worst one, meaning the highest CO2 reading, is going to dictate what the outside air damper does. If we can satisfy your set point for CO2, obviously everybody else who has a lower CO2 number is being satisfied as well. So that's kind of how that works. Every CO2 sensor has the ability to override the outside air damper. Andy asks, does that imply that a VAV damper could go to 0 CFM when there's not temp load or vent load? You could set it up that way, Andy, but you're not going to want to do that because we still need some ventilation for taking care of the non-people related sources in the building, like off-gassing of carpets and so forth. So we will have a minimum on there. The minimum, and maybe I could probably try to explain this. So when you look at ASHRAE 62 or the mechanical codes, on a current mechanical code, you have to provide a CFM per person plus a CFM per square foot, right? So there's 2 numbers that you do with the code and you add them together. The entire reason that we switched the ASHRAE standards to the per person plus per square foot was so we can do demand-based ventilation systems. So the per square foot number we leave alone, and that becomes our base ventilation rate, and the per person number of the code we're allowed to modulate down. So for example, if this particular conference room was required to have 300 CFM total for a normal job, when I put DCV on there, maybe I'm going to modulate it between, say, 100 and 300 CFM, 100 when no people are there, because I still need to take care of any off-gassing of equipment. And I can't tell if just for sure nobody's there or not. At nighttime, you could let it go fully shut because it's technically unoccupied then. All right. And I think that answers Greg's question. Does that mean CFM per square foot is needed at night if the building is unoccupied? No. You only have to bring ventilation air into spaces when they are technically occupied. However, during the daytime when this conference room is technically occupied, but I have 0 people in there, I don't know for sure if there's 0 people in there. I'm just not having enough people in there breathing that I can measure them with a CO2 sensor. So there could technically be 1 guy in a giant room. So I do have to ventilate spaces during the daytime, and I'm allowed to modulate that based on how many people are in the room. At nighttime, I can go fully down to 0 and shut all the zone dampers and air handlers for ventilation purposes. And no, you don't have to do any special flush in the morning there, Greg, for the building. That can be taken care of by the CO2 sensors when people come in, although many of us do like to program a 15-minute flush sequence to bring in the full ventilation air in the morning just because it seems like a logical thing to do. But technically, you don't have to do that. All right, so let's look real quick at a couple studies, and then we'll switch over to the code discussion. There's a lot of studies out there on indoor air quality, CO2, productivity, sickness, all that stuff, and kind of linking them together. I'm not going to read all these to you because it's kind of boring, but I'll show you some of them. Every one of these studies I'm going to show you is 10 plus years old. This is all old news, but it seems like every time I talk about CO2 and I don't mention the research stuff behind it, people ask for that. So this has been something that's been in the making for a long time, since 1998, 1999, when we really started pushing CO2 technology. So just a couple quick ones here. If my mouse works, and it does not want to work, what's going on? All right, there we go. So some of these studies, why is it not doing it? There we go. So here's the first study to show on here. This is a DOE Lawrence Berkeley Lab study where CO2 was specifically monitored, and the higher the CO2 level in the space, the worse productivity there was from the occupants. Productivity in this study was measured as work output of office workers or school scores on grades for students. So the higher the CO2, the worse performance, and hence you can imagine the lower the CO2, the better the performance. So ventilating the right amount of air is pretty key here. This is one of my favorite surveys of all time because they do it every year, the real estate folks do, and they survey why do people not renew their leases in commercial office building. And the number one reason always seems to be I'm too hot. Number 4 seems to be I'm too cold. Number 2 is always something related to ventilation, like it's too stuffy, it's too drafty, those kind of things. And number 3 always seems to be something related to elevators, but I'm not sure what the deal is there. But 3 of the 4 things are HVAC related. I'm too hot, I'm too cold, and it's too stuffy. That's why people leave buildings. So the better job we can do of conditioning buildings and ventilating them, the more likely it is we can keep our tenants and perhaps higher lease rates. There's another one, US EPA study. Like I said, I'm not going to read them all to you. This one was a good one because it correlated to money. Every dollar they spent to fix the ventilation systems saved $2 in sick time. There's tons of them out there. ASHRAE did a whole thing with the Massachusetts Technology Collaborative 7-8 years ago on studying American schools. And basically, a good chunk of the population, students and teachers, are in a school all day long. And many of those schools are considered below average. USA Today just published a website, and you put in your zip code, and for your school at your house, it tells you how bad the air quality is around your school, let alone the air quality that's being sucked into the louvers. So there's lots of studies like that. I'll leave them on here for reference. Here's the ASHRAE Journal from 2006, directly relating outside air intake to productivity of students. There's a bunch of them out there like that. So all that stuff happened pretty much in the late 90s, mid 2000s, and that really drove what we did with the standards and codes. So nowadays, demand control ventilation is allowed by just about every mechanical code. In fact, I can't think of a mechanical code that does not allow it in any municipality or state. It's been in ASHRAE 62.1 for years. It was an addendum in 2004. It's been in the permanent standard since 2006. And as you know, the mechanical codes basically just cut and paste whatever ASHRAE does. And the local codes either adopt the international code or they write their own, but most of them still cut and paste the same language. So specifically, in 1999, ASHRAE 62 came out and said that the ventilation rate procedure could be handled dynamically, changing the ventilation based on a demand basis. That actually became part of the standard as an addendum in the 2004 version, as opposed to just an interpretation. International Mechanical Code since 2006. And here we are today with the current mechanical codes. So this is ASHRAE 62.1 2010, which is identical to IMC 2012. And this language has not really changed in the past 6 years. And this is specifically allowing you to change the ventilation rate for demand control ventilation system and reduce the outside air below the normal code minimum. And then in number 1, in the example, it specifically cites CO2 as the main method to do that dynamic ventilation. It's called dynamic reset in the code. Chicago comes up a lot because it's, special area. They always got special codes, a long history of doing their own codes. And in this case, Chicago was actually cutting edge. Chicago's had it in the mechanical code, or rather the ventilation code, since 2003. So they beat ASHRAE by a couple years on getting it into the code, allowing you to modulate the ventilation rate based on CO2 sensors. The only thing that's unique about the Chicago code is that you have to use an indoor set point of 1,000 parts per million, whereas with ASHRAE and the International Mechanical Code, we're using a differential between outside and inside, and usually we're looking at 700 parts per million between outside and inside. So if it's 450 outside, that usually means inside our set point would be 1150. Chicago, we have to do it at 1,000 parts per million indoor set point. So we don't get quite the same energy savings with Chicago, but we still get a pretty substantial energy savings. Wisconsin's the other one that comes up all the time as being a little bit unique. And we used to talk about what was in the code there, but then the code changed in 2011, which made it a little bit more easy to explain what you have to do. And basically, the section of the code that I chose to put on the screen and highlight here in that first section tells you that you're allowed to modulate the ventilation rate. The minimum required outdoor rate may be reduced in accordance with such engineered system design. So basically, the engineer can approve to have the code reduced below the normal minimum and following the International Mechanical Code or ASHRAE 62 or some other governing standard to figure out what those numbers need to be. However, in Wisconsin also, one of the amendments to the code is that, and you can see there in number 5, that there's only 7.5 CFM required per person anyway, which is a lot less than a normal, say, Illinois, Minnesota, Indiana building were providing somewhere between 10 and 20 CFM per person. So it's already really low outside air level. So modulating the CO2 sensor does not have the same bang for the buck as it does in other states, but you can still do it. And in places that are densely occupied, like movie theaters and gymnasiums and stuff like that, it makes a lot of sense. Other spaces like an office, it might not have the payback story in Wisconsin because the outside air rate's already much less. So not only is it allowed by all the mechanical codes, like I said, I can't think of one code that prohibits it. It's actually required by most energy codes. And by most, I mean all. I've not seen any energy codes, current energy code, that don't require it as well. So specifically, my mouse back here. It's been in ASHRAE 90.1 for several years. That feeds into the International Energy Conservation Codes, and that typically gets adopted by local states and or municipalities. So the current code is ASHRAE 90.1 2010. Which feeds into the International Energy Conservation Code 2012. What I'm showing you on the screen here is a version that's 3 years older because most of the people on this call are from a different state than Illinois. So I'll talk about them all individually. So Indiana files 90.1 2007 exactly. So it's exactly what it says here on the screen. If you are from Wisconsin and Michigan, like several of you guys are, you file the International 2009 code, which is the exact same language on this screen as well. So Indiana, Michigan, Wisconsin, this is your code. If you have a space that's larger than 500 square feet, so conference room, training room, open office, cubicles, classroom, that kind of stuff, and the population density is more than 40 people for every 1,000 square feet of space, you are required by law to put a demand control ventilation system in. Now there's exceptions on there for really small systems or for old pneumatic VAV systems and things like that. But for your average, rooftop job or whatever, this is when you're going to have to do it. So that's the case with that. With Illinois, we are now on the International 2012 code. We adopted that in January. We're the first state to do so. The language is exactly the same as you see on the screen for Illinois, except it's not 40 people per 1,000 square feet. It's 25 people per 1,000 square feet. So this means that it's code required more frequently than in the past. So not just classrooms and gyms and auditoriums and movie theaters are going to get nailed. It's going to be some of your regular office spaces and stuff may, depending on the cubicle density, may have to do it as well. It's also in standard 189.1. If you're in an area that's following that. A lot of municipalities don't adopt that as their code, but some government buildings do, and it is in there as well, listed specifically. And I point this one out because this is one of the standards that specifically prohibits it from being in the return air and says you have to put it on the wall between 3 and 6 feet, which is the breathing zone. You're going to see things, if you don't already know, stuff that's in 189.1 eventually makes its way into 90.1, which makes its way down into the codes. So I expect fully that in 90.1 in the next cycle, you'll probably see return air CO2 sensors specifically pushed out of the discussion, and you'll have to put them on the wall between 3 and 6 feet. If you're doing a LEED project, the 2009 version of LEED, which is still the current one, even though we got drafts of the 2013 out there, CO2 sensors are allowed for EEQ credit 1, but you do have to mount them on the wall between 3 and 6 feet. You're not allowed to put them in the return duct. And they're already triggering theirs based on the 25 people per 1,000 square foot rule. Tony asks what the ventilation rate requirements are for a data center, and I actually have no idea, Tony. We have to look that up later. I'm not sure. Andy asks, can you speak to avoiding over-ventilation, like keeping CO2 between 800 and 1,100 parts per million during occupied times? We see plenty of spaces like 400 and 600. Yeah, we could talk about that, Andy. What Andy's asking, there's two different things that could happen. On a constant volume system, like with a regular rooftop or air handler, with one duct system, constant speed fans, no zone dampers, and one CO2 sensor on the wall, it's pretty easy to keep it in the target range of 1,000 to 1,100 parts per million, 1,200 parts per million. If you see it lower in those spaces, it's one of multiple scenarios. One, it's an economizer day outside, and I'm trying to get free cooling. Great. Give me the free cooling. If I overventilate, that's fine. I'm getting free cooling. I don't care. Right? So that's totally normal, and that's totally fine. The other thing is that they might have put a too low of a set point in to begin with. For some reason, like to Andy's point, I keep finding people that put 700 parts per million in as the set point. And I think that's just a function of them not understanding their own controls device. Usually we're trying to be 700 above the outside air, but somehow they've interpreted it to mean they need to be 700 inside. If it's 700 above and it's 400 outside, that really means 1,100 inside. That's one that causes it to happen quite a bit. And then the other thing that happens is on zone systems, we have to bring in the air to take care of the worst case zone. So that may cause some of the other zones to become over-ventilated as well. Now, when we're saying over-ventilated, we're not bringing in more air than the regular code would have said. We're still bringing in less than the regular code's outside air. We're just bringing in more than we actually have to with the CO2 system. At no point in time are we going to bring in more fresh air than the regular code with non-CO2 projects would have had to bring in anyway. So if the regular code said bring in 1,000 CFM for this project, I'm going to modulate it between, say, 300 and 1,000 CFM. I'm not going to go above the 1,000. The old code minimum becomes my new set point maximum. All right, so it's allowed by the mechanical codes. It's required by the energy codes for certain densities of occupancy. But there's also tons of places out there where it's not required, but I can get some pretty substantial benefits for doing it. And we'll talk about the energy benefits here in a minute and how to calculate that and what kind of savings you can expect. But even without the actual energy utility bill reduction, many of the utilities are incentivizing this to save energy. So if you didn't realize already, most utilities, especially in the Midwest here, have state laws that require them to have energy efficiency programs. They charge you, the ratepayer, a certain amount on each monthly bill, and that goes into a big giant pot. And then that pot is used to pay out energy incentives for people that upgrade their furnace, put in a better chiller, improve their boiler plant, or in this case, add CO2 sensors to their ventilation system and reduce the outside air. So these are some of those typical ones. So for you guys that are in Illinois, on the electric side, so if you have ComEd Electric in the Chicagoland area and suburbs, it is 3 cents per square foot. Now what I did, just so you know, is I made all of these in a per square foot basis. A lot of them do it in, per 100 square feet, per 1,000 square feet. To make it consistent, I just made it per square foot and moved the decimal place. So for ComEd, if you're a ComEd customer, commercially speaking, and these are all commercial, by the way, it's 3 cents per square foot is your rebate from ComEd, which is a pretty decent rebate on the electric side, considering we're in a heating-dominated climate. You get your rebates through ComEd or through the gas utilities if you are a private building. In Illinois, if you are a public building, like a fire station or a public school or a village hall or a federal building, you do not get your rebate from the utility. You get it from the Department of Commerce and Economic Opportunity. That particular program does take into account gas and electric, and they pay you between 28 cents and 40 cents per square foot for the CO2 sensor, depending on what kind of system you have, electric heat, gas heat, etc. So there's a little bit range there for those kind of buildings. That is by far the largest rebate that I've seen for the gas and electric added together from anywhere in the Midwest. So that's a very substantial rebate. If you work with public sector customers in the state of Illinois, you should be all over this. This thing pays for itself in months. If you're over in Northwest Indiana and you have NIPSCO gas on the gas side, and it's 15 cents per square foot is the rebate for CO2 sensors. For you guys over in Michigan there, I know we do a lot of work in Southwest Michigan, and the utilities there on the gas side are Michigan Gas and Semco Energy. And on the electric side in Michigan, it's Indiana Michigan Power. On the gas side, on the Efficiency United program, it's 8 cents per square foot. And the electric side, it's 2 cents. So if you have both gas and electric utilities that qualify, it's 10 cents per square foot combined. And for you guys in Wisconsin, it is actually 5 cents per CFM. So it's a little bit different. It's not per square foot up in Wisconsin. It's 5 cents per CFM to do CO2 sensing on your air handlers and stuff like that. If you are doing the rooftop optimization program as part of that program in Wisconsin, instead of the 5 cents a CFM, it's a flat $350 per rooftop. So that works really good on small rooftops. If you got a 7.5 ton rooftop, get $350 straight up is a pretty substantial rebate, and that'll basically pay for the sensor, and then you're just paying for some labor to install it, etc. There are a couple other utilities that do look at CO2 sensors, although they don't do it on a prescriptive basis. So the ones I just showed you, it's prescriptive. You put in the CO2 sensor per the rules of the plan, fill out the application correctly, you get this much per square foot or CFM or rooftop or whatever the program was. Other utilities don't have it listed out specifically yet. So specifically right now I'm talking about Nicor Gas in Illinois, Peoples Gas in Chicago, and North Shore Gas up in the eastern half of Lake County, Illinois. They don't have it as a prescriptive rebate, at least not today yet. It is a custom rebate, which means you can apply. A custom rebate means you can apply for anything you want that saves energy. You calculate how much energy it's going to save. The utility looks at it and says, yeah, we agree with you, or no, we're going to tweak it. And then based on how much you save over the first year, they pay you based on that. We're working with all three of these gas utilities to get this as a prescriptive listing for the next program year starting in June. Things just are not finalized on that, but hopefully that goes forward and you'll have something similar to these where you're getting paid 8, 10, 15 cents a square foot or something like that. But right now it's a custom thing for the gas utilities in Illinois. If you have more questions about that, chat with me later on offline. All right, any more questions while we're going here? Let's see. All right, looks like we're all caught up on the questions for the moment. All right, so kind of the goal of this here is we want to ventilate to the actual occupancy versus the assumed design occupancy. If you're not there, I don't have to provide ventilation air for you is kind of the goal here. So we're trying to eliminate the overventilation. Instead of just getting everything, we're getting whoever's there. The paybacks are pretty good. We're going to talk about that in a second here. You save quite a bit of energy. So first here, let's look at a typical building. And this actually is not data from a typical building. This is from a building in Florida from a study like in the late 90s, early 2000s. But every single building I've ever looked at since is similar to this, and I'll explain that in a second. So on this chart, we're going from midnight to midnight on a typical day, and we're going from 0% of the design airflow up to 100% of the design airflow. That's not 100% of the outside air damper's movement. That's 100% of the design CFM. So I figured out the regular code said bring in a certain amount of air. Let's just say, for sake of argument, 1,000 CFM. Great. 1,000 CFM is what I got to bring in. So come, what is this here? 7 o'clock in the morning, we turn the system on. I provide 1,000 CFM of air per the regular ventilation code. And then, what is this here? Say, say 6 p.m., we shut off the ventilation system. Boom. Then at nighttime, it really kind of cycles on and off, because if you didn't already know it, on a normal air handler, the outside air damper on a rooftop, every time you call for heating and cooling, that outside air damper goes wide open. Or not wide open, it goes to ventilation position, because the rooftop has no idea that it's not ventilation time. If you've got an advanced DDC system that's taking direct control of the actuator, that is often changed and you make it 0 CFM. But on a rooftop, the rooftop doesn't know it's night or day. It just knows the fan's on. And if the fan's on, it goes to ventilation position. So that's why we're showing it like that with the green bar here. So some systems may go all the way off. This one's a little bit different because it's like a rooftop type job. The purple drawing here shows you what happens if you put CO2 sensors in. And like I said, this is from a real building. So when everybody starts coming in at 7 a.m., all the employees don't come in at the same time. They kind of trickle in at their various starting times, or depending on how early they are or how late they are or whatever. So the CO2 sensor is tracking who comes in when. So you can see we're not turning on quite as quickly as the green bar would have been. We ramp it up and modulate the damper open as opposed to going to a fixed position. And you can see by whatever this is here, I don't know, we'll call it 9 a.m. Most people kind of made it in for work. A lot of people come in late for some reason, but they all didn't make it in, right? Some people never came in at all. And then at whatever this is, 11:30 or whatever, they start cutting out early for lunch, which is pretty common. Some of them leave the building for lunch, some of them stay, so that's this valley right here. Most of them make it back for lunch, but not all of them. And then around what is this here? Around 3 o'clock in the afternoon, they start trickling out of work early. This is a typical office building. This is pretty much every building that you look at. It's not abnormal at all. So my energy savings potential is everything that's inside this green bar. Instead of ventilating up here at the peak, I can ventilate down here on the purple. So Andy's just pointing out in his question that this green bar here represents the design maximum CFM that I would have to bring in, right? Or on a non-DCV job, my code minimum. And the purple is my actual occupancy and hence my actual ventilation air. So everything in the green is just pure savings. Over here on the right-hand side are some drawings that are similar out of the FEMP study. Every building we do is a very similar profile. Every office building has what we call the two-hump profile, the crowd in the morning, then we miss a bunch of people at lunchtime, and then the crowd in the afternoon, and everything in between is available. Now, it's not that everybody in your building is not showing up for work, although that could be the case, or maybe some of them are outside employees, like salespeople or whatever, so they're only there certain hours. But also, we have to ventilate every room for the full design occupancy. Well, when you're all in your offices, no one's in the conference room. Hence, we really don't have to ventilate that conference room if we knew you weren't there with a CO2 sensor. So it's not always necessary that everybody's not there. It's that they're all moving to different rooms, and we only have to ventilate the room that you're in. The bottom drawing here shows a typical restaurant. It's what we call a three-hump profile, breakfast, lunch, dinner. And there's also always like a secondary hump after each meal. This is like the people that don't want to go to lunch when it's crowded, I guess, or something. So there's always that secondary hump crowd that comes out. But every restaurant we do has a similar profile. So most buildings we can track like that to see how it works. This is based off of cumulative study data. I believe this came from Telair, who is now GE Sensing, which is a CO2 sensor manufacturer. What we're showing you here is for different building types, on average, what do we typically see in savings? So up here along the top, 100%, that's what if I would have just brought in the regular amount of outside air required by code and I had no CO2 sensor. The yellow is representing what I brought in on a CO2 sensor job. So for this office building, I'm basically cutting my outside air back on average 25, 28%, right? Cutting him back. And you can kind of believe that based on how many people show up, and the graph I just showed you that some of them are not there at all times. They move around from the building. That one's pretty straightforward, and most people get that one. The rest of these ones are the ones that are kind of shocking to people. The restaurant one, for example, the retail one, for example, I'm basically cutting the outside air back on average 90%, right? That doesn't mean that this building's only 10% occupied. It just means it's 10% occupied on average, because a retail environment is probably designed for a peak crowd that's, well, it's probably like Black Friday, right? How many people am I going to ever get in this store on a maximum day? And that's my ventilation rate, and that's what I ventilate for. Well, if those people don't all come on Tuesday at 9 a.m., well, then I don't have to ventilate for them. So all the hours of the year that I don't have everybody maxed out in the building, I can cut back the ventilation rate for those hours. And it ends up being really substantial on a retail project. Restaurants are similar. They're designed for a peak day, and it's probably the Saturday night dinner crowd, right? So, but there's less people there on Wednesday night. There's certainly less people there on Wednesday at 2:30 in the afternoon, right? So I got all these valleys on the restaurant when I'm not at peak design, and I don't have to bring in peak airflow when that's not happening. And then the school one really takes some explanation, because people see this and they're like, wait, 70% of the time my kid's not even in school, right? So that doesn't make sense. My kid only misses 5 days a year or whatever. Well, there's a couple things going on with the school. One, the school, each classroom is designed for a certain number of kids, say 35 kids. Well, if the class only has 30 kids this year, I'm already overventilating for 5 kids, right? So that's part of it if my classroom's not maxed out. Although nowadays schools seem to be pretty maxed out. But if they weren't, that's part of the discussion there. Then there's also the kids that are sick, right? So they never make it to school that day. And there's always 2 or 3 kids every day that don't seem to be in the classroom. But that still doesn't account for this 70% reduction. This big difference, the 70%, right, that comes from the fact that the kids are not always in the classroom. If you got kids that are in grade school or junior high or whatever, and you look at their schedule for the day, yeah, they're in the classroom for a couple hours, then they go to the gym for an hour, right, then they go to recess, then they go back to the classroom, then they go to the lunchroom, then they go to the music room. So they're constantly moving around, and their classroom is not fully occupied all the hours of the day, right? They're only in, on an 8-hour day or 7-hour day, they're probably only in their classroom for the hours. Same thing with the gym and the lunchroom and the music room and all those other places. They're not fully occupied all hours of the day. The kids are moving them throughout the building, right? And everybody's got to be somewhere in the building, but you can't be in 2 places at once. So if we can figure out where you're not at, we can cut back the ventilation rate temporarily for that particular space. That's kind of the idea with the schools there. It's a very large potential savings. Here's some sample savings around the country. So just to give you an idea, paybacks are usually pretty quick. The more densely occupied the space is, the faster the payback is going to be, and the more volatile the head count is. So the more people that are in the building today but not there tomorrow, or there this hour, not there the next hour, the more volatile the head count is, the more often CO2 is going to pay for itself. So like a church, for example, is like the best scenario you could possibly have, right? They got maybe 2 services on a Sunday, maybe 1 or 2 on a weeknight that are not fully occupied on the weeknight, and all the rest of the time they really don't have hardly anybody in there at all. So that's a very volatile thing. There's 1,000 people in the building, then there's like 3, right? So a church is a fantastic example. Movie theater is the same way. 200 people file in to watch a movie for 2 hours, then for the next hour there's like 0, or there's 3 guys cleaning up or something like that. So those spaces are fantastic for this. There are tons of studies out there. At some point in time, we stopped tracking the studies just because there's so many of them out there. And it's pretty well-proven technology, and hardly anybody wants to argue with me about it anymore. Back in 2000, there was a lot of pushback, and people didn't want to design around it because it wasn't well-defined in the codes. But now that it's in all the codes, it's in the utility rebate programs, it's pretty clear-cut what you need to do and how much you can save. A couple questions came in. We'll see if we can address those real quick. Paige asks, from a savings standpoint, what about high-rise type office buildings like downtown Chicago and high-rise condos in the common areas, typical to your office data? Yeah, so in that example, Paige, your high-rise office buildings, that's this exact same kind of scenario here on the left, exact same kind of story here. High-rise condo buildings are a different discussion. Even though you're talking about the common areas, you probably can't do any CO2-based demand control ventilation in those condo buildings because the common areas typically are handled with some kind of makeup air unit that's pressurizing the lobby and the hallways, and that air is expected to pressurize those hallways and then leak under the doors into the condo units and then get sucked out the individual bathroom exhaust fans. So since you really can't track what's going on with the individual people in the spaces, this is really not applicable to residential, even residential high-rise, which is similar to commercial. But for office buildings, absolutely yes, similar to this data over here. And then one more here. Ken asks if CO2 sensors require frequent calibration. Is that true? Ken, I'm going to make you wait 5 more minutes, and we're going to address that specifically. The answer is yes and no, depending on the kind of CO2 sensor that you're utilizing. So we'll talk about that in just a couple minutes. There's a bunch more case studies in here. In the interest of time, I'm not going to read through them all, but some of them are reasonably high profile. All of these ones that are on here right now I'm showing you are more than 10 years ago installed, because this is a well-established thing at this point. But these are some of the more higher profile ones here in the Midwest area. All right, so the actual way that we control these guys, first thing you got to do is figure out if CO2 is appropriate. So like I said, you got to figure out how much air you need just to pressurize the building and make up any exhaust you have coming out. You got to look at the codes to see what's allowed and or required, and then you got to think about, do I have anything weird going on in terms of hazardous materials? An office building, you probably don't have that, right? But other spaces, you might have things like manufacturing and process things, and we'll show you a chart here. So looking at this chart on the screen, this is a chart that one of the sensor manufacturers came up with about 10, 15 years ago, and it's still pretty applicable today. If it's on this chart and has an A, that means it's a good idea for CO2 sensors. C means it's a bad idea. B means we probably got to talk about it and see what you're really doing. So for example, some of the A's that are good: classrooms at a school, perfect; music rooms, libraries, auditoriums, all excellent candidates. Any indoor sporting arenas, excellent candidate right there, right? It's one of the best ones. Office buildings are great. Retail is great. Someone asked earlier about hospitals. Depending on what area of the hospital, lobbies and waiting areas are okay. Some of these other ones you're going to want to avoid. Hotels are great for the conference room areas and ballrooms. Ice arenas, which is kind of like an indoor stadium, those are fantastic ones. Gymnasiums at schools are fantastic ones. I don't know if anybody still goes to the disco, so you can tell how old this chart is, but you know, any type of nightclub or dancing venue where there's no smoking involved, fantastic candidate. Bowling alley, if there's no smoking, fantastic candidate. Movie theaters, right? So any of these kind of spaces are really good ones. The ones that are bad are typically ones where you don't have people coming and going, or there's some kind of chemical involved. So a guard station, he's bad because hopefully somebody's at the guard station at the prison. Otherwise, people are leaving, right? And that's not good there, right? Dry cleaners are bad because we're not really ventilating for people. We're ventilating for all those chemicals that are involved. Locker rooms are horrible because locker rooms stink in general, even when there's nobody in there, right? They stink just because of the hockey gear and all that crap. So you don't want to mess around with the locker room and cut back their ventilation. Kitchens are problematic because we are bringing makeup air in to make up the exhaust hood, not for people. Vehicle spaces are okay for demand ventilation, just not for CO2 demand ventilation. In garages and vehicle repair bays, we use CO, carbon monoxide, for cars, and NO2, nitrogen dioxide, for diesel vehicles. So you can still do DCV, you just can't do it with a CO2 sensor. Pet shops are horrible because pets stink even when there is full ventilation, right? So some of those kind of things, FDA processes. Warehouses are bad because you have this huge volume of air and like 3 employees, so you can't even measure the CO2 because of the volume of air that's involved. Stay away from the medical operating procedures and things like that. What else? Swimming pools are bad because of chlorine. And then all the B's are the maybes because we don't really know what you're necessarily doing, right? So like a maybe would be what's a good one here? Like a dining room, for example, right? The dining room is actually a fantastic case in a restaurant if you're not using the dining room to steal air to make up the kitchen hood, right? If you are, then it's a bad idea. Same with the cafeteria and bar discussion. The bars, are they smoking or not smoking? That kind of makes the answer happen, right? Some of these other ones, well, what kind of chemicals do they have going on? I need to know those details before I can make those decisions, right? Casinos on here because of the potential for smoking. All right, so that's kind of some of those guys here, when you might want to use this. So once you decide if it's appropriate or not, this is kind of how you set it up. Here on the top would be the normal code required ventilation rate up here, right? Not 100% of the damper, but 100% of the design ventilation rate if I did not have a CO2 sensor. Well, now I'm going to modulate it, but I still need some basic minimum. It's typically going to be 20 to 30%. The place I get that number from is the ASHRAE 62 or the International Mechanical Code. Like I said, they give you a CFM per person and a CFM per square foot number. The CFM per square foot number becomes this base minimum here. So that CFM per square foot is what's going to be my absolute minimum. And then my people part, my CFM per person, I'm going to modulate up and down here throughout the day, right? So this was my old code minimum on top. Now I got my new CFM per square foot portion on the bottom. So the CFM per square foot plus the people would have been the code. I'm going to modulate below that. And that's something else I want to point out. With the CO2 sensors, there's a misconception that I'm going to be bringing in more outside air than I might have normally would. That's not what this thing does. It's designed to bring in less outside air. I'm starting with the code ventilation minimum as my top end. I'm going to modulate him lower if people don't show up for work that day. That's kind of the idea here. The only time I'm going to go above that is if it's an economizer day, right? Then I might go above him if I want to bring in some free cooling, but that's different. That's a different animal, right? So that's how I determine the ventilation rate. The current code is CFM per person plus square foot. Move along here and skip a little bit ahead. The kind of set points that I want are depending on the activity level in there. Like I said, for a typical office building, it ends up being a differential between outside and inside of 700 parts per million. Normally, you're going to probably register about 450 parts per million here in the Midwest. That means my indoor set point is 1150, right? That's kind of how that works. And this chart over here just gives you a little bit of a scale on what's good and what's bad if you walk into a building with a handheld meter, right? So someone asked earlier, they see these buildings at 400 to 600. I think who asked that? Andy asked that, right? 400 to 600. So they're down over here, significantly overventilated, huge waste of energy. 600 parts per million of CO2 is probably like 35 CFM per person ventilation rate. It's a huge amount. So those are definitely candidates to reduce the outside air. But if you go somewhere else and it's 15, 18, 2,000 parts per million, you can see down here they're underventilating, right? And we said Wisconsin code is 7.5. So if you go into a job in Wisconsin and they got 1,800 parts per million or higher, that's going to be a red flag that they're underventilating it. In other parts of the country, 10, 15 CFM per person, so you're over here at 1,200, 1,300 CFM per person. Normal design rate, between 1,000 and 1,200 parts per million is my normal target rate for being ideally ventilated. City of Chicago is 1,000 fixed, and then in the suburbs it's the 700 differential, so we're more like 1,100, 1,150. So hopefully that kind of answers that. Keep on moving here. There's a couple different methods of control. There's the old school way, which is relay control. I got a CO2 sensor on the wall. I tell it when you get to 1,200 parts per million or whatever the number is, you close a relay and tell me something bad happened in the space. When I see that relay close at my damper, I'm going to go ahead and open my damper back up to the code, right? So what I end up getting is like this ping-ponging effect if I do the relay control. So up here, once again, 100% is my normal code minimum. I get to drop down below that code minimum when I'm not measuring high CO2. Then I got to ping pong back up, then down, then up, then down, up, then down. I'm basically flopping the damper, in this case, between 20% of CFM and 100% of the design CFM, bouncing it back and forth. It's the old school way of doing it when the economizers didn't have CO2 inputs. Now they do, so now we can use PID loops or at least proportional loops. Proportional is very common and very cost effective to utilize. So the way that basically works is I can tell it two values. So up here is my my top value, which my code design airflow. That's this line right here. If I did not have a CO2 sensor, how much CFM would I have to bring in? When I have more than 700 parts per million of CO2 above the outside level, I'm going to go ahead and bring in the code required airflow for as infrequently as that happens. Then I'm going to pick a lower number. In this case, I'm picking 100 above the outside air level. So in case 400 plus 100 is 500, I pick that guy. Then I can draw a straight line between them, hopefully straighter than that line. And any point in there, I can figure out what it's going to be. So if I got, I don't know, whatever, 700 parts per million differential or inside, I need this much outside air. If I got, I don't know, whatever, 900 parts inside, I need this much outside air. If I have 1,100, boom, I actually need the regular code airflow. So that's a proportional type control, and that's very easy to set up, and a lot of rooftops have that, and a lot of air handler BAS systems have that. It's pretty straightforward and easy to do. The next step beyond that would be a PID loop. Here we're just showing a PI loop, proportional integral, because we don't frequently use the derivative term for HVAC because HVAC systems react slowly anyway, so we don't need to calculate that fast. But all a PI or PID loop really is doing, it's doing that same curve like I had there a second ago. It's just predicting how fast or how slow I'm getting to my set point and then trying to adjust the curve. That's really all a PID loop really does. It tries to predict the rate of change, or actually measures the rate of change as it's happening, and uses that to calculate a new setting to kind of proactively get there. It's kind of like cruise control in your car. You hit the resume button, and your car, immediately guns it from 40 miles an hour back up to say 65. But as it gets closer to 65, it starts backing off the gas pedal automatically. It's exactly what we're trying to do with the PID loop, to get up right there to the set point and be nuts on. CO2 sensor locations, like I said earlier, return ducts are bad choices because it ends up giving you an average. If it's a zone dampered system, you absolutely cannot use a return air CO2 sensor because it's going to give you an average and it's not going to tell you which dampers to open for which rooms. Putting it on the wall is a much better choice. A wall sensor in an open floor plan area like an office cubicle or a auditorium can handle about 5,000 square feet. When you get further than that, the distance that the CO2 molecules have to travel makes it react too slowly for us to modulate the damper correctly. So if you had 10,000 square feet, you would use 2 sensors together on the same large zone, like a sporting arena or something like that. You want 1 CO2 sensor per zone, and a zone on a VAV system is defined as a VAV box for our purposes today. On a constant volume system, it would be anything within a partitioned wall. All right, so those are just some kind of guidelines for that kind of thing. All right, so the last thing we'll talk about here, and these cheat sheets are on there so you guys can see them if you want all these pages. These are the typical economizer controllers that have CO2 sensors built into them already based on the model number and what they look like. Most rooftop manufacturers over the years have used Honeywell controls. Most of the air handler projects will have DDC controls probably installed on them. But for the rooftop stuff, the ones that say indoor sensor input and have it in green over here, those guys can all do it, right? So the new Jade controller from Honeywell, which is the only one they still make, by the way. Honeywell has discontinued all of their other models of economizer control. So all new stuff has this on here. They can all do CO2 sensor readings. The 7212, which is extremely common in packaged rooftops from Carrier and other folks, can all do DCV control. The 7215, which is a little bit older one, can do it. The 7459, which is what you will find in a lot of rooftops 10 plus years ago, that guy does not have the ability to do it. So that just gives you some ideas on ones you see in the field and whether they can automatically control a CO2 sensor or whether you got to retrofit the controls. We'll skip some of this stuff in the interest of time. This is not a new idea. CO2 has been in standards and codes forever. Literally like 100 years ago, they started putting CO2 references in some of these design manuals and things like that, referencing, in this case, 10 parts for every 10,000, which, oh, by the way, is 1,000 parts per million, which is pretty much the same target number we use today. Those CO2 numbers, through all those handbooks and codes and ASHRAE, those CO2 numbers are what ended up dictating the ventilation rates in the VR procedure to begin with. So it's not that CO2 is being now permitted by the codes, it's that CO2 actually really formed the codes. You just didn't know that that happened in the background on the calculations when they set up the numbers. So there's the history of CO2. We'll kind of skip over that, but it really got active in the 90s and 2000s and became very code accepting in the 2000s, by name, if you will. Why it's popular now, like I said, the mechanical codes specifically allow it and the energy codes strictly require it. That's why it's become so popular. The other thing is that this stuff has gone down in cost significantly. We stopped kind of tracking it because it's kind of leveled off these days. It doesn't change much anymore. In fact, sometimes it even goes up a little bit, but we're still around this same type of cost for these sensors. If you're just installing one CO2 sensor on a packaged rooftop, you're not getting that for $400 or whatever this is showing you here. That's going to be more like $600-700. But if you're doing a whole project, that's when you can get the cost down below $500. So it can be fairly cost effective if you're already doing other work in the space anyway, kind of thing. The other thing is the reliability has significantly improved. The CO2 sensors that we use at our office are from 2 different manufacturers. We use the Carrier ones, which are manufactured by GE Sensing / Telair, and we use the Honeywell ones as well. And both of those have automatic calibration routines on them. So for example, the one I'm showing you here is a Telair sensor. It has a 15-year design life, and it has a 10-year calibration guarantee. If it goes out of calibration in 10 years, they just give you a new one for free. No questions asked. That was, I think, Ken's question, if they go out of calibration or not. I've literally done thousands of these personally, and I've only, in my memory, can recall ever having to replace 2 of them for calibration reasons. So this thing is pretty reliable. In order for it to do the automatic calibration, it basically has to go unoccupied for about 4 hours a week. Almost every building you do has at least 4 hours of unoccupied time a week, maybe short of a 911 call center or something like that, or a prison. All the other spaces are going to have that, offices, schools, and so forth. So what it does in those 4 hours is enough time for air to leak in and out of the building envelope naturally, for these sensors to stabilize themselves to a CO2 level that's matching what's outside, and the outside air levels are very consistent throughout the day, night, and year. So they basically calibrate themselves to the leakage of the outside air, if you want to think of it that way. Here are 3 sensors sitting side by side in a test chamber for the course of like 5 days, and you can see they start out a little bit far from each other, 50, 60 parts per million apart, and then over time they kind of honed into the same number. Same 3 sensors over 2 weeks. Likewise, they kind of came to become the same number by calibrating themselves, and the same 3 sensors over the course of 3 years. This calibration thing definitively works. It works so well that our sensor manufacturer started taking the calibration buttons off of their hardware. There is no longer a way to calibrate it. It's literally impossible. And the reason they took the button off there is because what people would do, they take the cover off the thermostat, they would see a button, and whenever you see a button, your instinct is to do what? You press it. Well, they would press it and basically zero out the reading because they weren't running CO2 or nitrogen through the thing. They'd zero it out, and then the whole thing would be jacked up. So now you can't even calibrate it. If it goes out of calibration in 10 years, you throw it away, and they would give you a free one under warranty. So to answer Ken's question, if you get one that has an automatic calibration routine, calibration's out of the discussion. You don't have to do anything with those guys. It makes it very easy to do. So here's our summary. We want to ventilate for the actual occupancy instead of the design occupancy. Who actually showed up to the building today? And not only that, who showed up to the building and what room did they go into? We want to track them and ventilate for them and not anybody else. And that helps us stop overventilating. Right? Anytime we ventilate to code and everybody's not there, we're overventilating. We want to make sure at the same time, though, that even though we're going to ventilate less, that we still ventilate enough to comply with the codes for the people that actually did come. And we want to make sure that we comply with the energy codes, which may require CO2 sensing depending on the density of occupants in this design space. And then we want to save people a crap load of money on the end. The return on investments and the paybacks end up being a lot better now that in the past couple of years we got CO2 sensing on the rebate programs from the utilities. So that helps the payback and gets it to be pretty attractive. There are a few other ways you can do it. You don't have to do it with CO2 sensors. You can track whether people are there or not other ways. One common way is with occupancy sensors. This is really kind of a go or no-go thing. It works well for school classrooms. Either the kids are in the room, and I'm going to ventilate for 35 kids, or they're not in the room, I'm going to ventilate for nobody. Yeah, it's true that you may have 28 one day instead of 35, and you don't get to capture that with the occupancy sensor, but you still get kind of close. So if you want to do it with occupancy sensors, it does work in certain applications, like a classroom. There's all kinds of other things you can do in hotels. Tie the ventilation into the key card. Are you in the room or not in the room? On larger, more complex office buildings with BAS systems, you can integrate to the security system. Did you swipe into the building or did you not swipe into the building? You're not there? Great. Let's turn off the ventilation in your office because you're not there anyway. Right? So there's all kinds of different ways we can do some of this stuff to kind of chop it down. CO2 sensing is by far the most common way you can do it. And the last thing I'll leave you with is there's a free software tool that works very well. The Honeywell folks put this together. If you want it, just Google Honeywell economizer savings, and you'll get this. If you can't find it, let me know. I'll send you a link. I also have a screen-by-screen cheat sheet that I made up that can help you walk you through it. We don't have time for it today. But basically, you spend 5 minutes putting stuff in, square footage, efficiency of your equipment, picking a default occupancy schedule for a school or office or whatever. And then it'll calculate your savings based on those technologies. I will just say, in this case, the reason it says the cost is nothing and the payback is nothing is I didn't put costs in here because I don't know, everybody's different depending on whose equipment they're using and what state they're in and whether they're an end user or a contractor. So I just left that out of the discussion for this purpose, but the software can do it if you put your costs in. And I just focused on the savings dollar amount on here. So the ones with DCV and the setback stat, DCV with the setback stat and economizers. The savings can get pretty substantial by putting these guys on. And you can do this without setback stats or with this example I happen to do with example with it. So this software is nice because if you're adding a programmable stat and an economizer and a CO2 sensor, it takes into account all of those things. Whereas if you calculated the 3 of those things individually and added them together, you would end up overestimating the savings for the client. This software takes into effect that these things interact with each other. And if the economizer is open for free cooling, I don't get the DCV benefit, for savings because I'm already getting the cooling savings kind of thing. So it kind of puts all 3 together and really kind of levels it out. All right, let's see if we had any final questions anybody typed in. I think I did a pretty decent job of answering the questions as we went. If anybody has any more, let's type them in. Andy writes in a comment that he's seen a few automatic calibration sensors in the field that are out of calibration. And could we mention the calibration or replacement period for those cheaper ones? At this point, the only sensors we use are the Carrier/Telair ones and the Honeywell ones, and they all have automatic calibration routines. I'm not sure where you can still get a one that has to be calibrated every year. Like those Honeywell ones, I mean, it's a couple $100 now. They're really inexpensive. A couple $100 to a contractor, then obviously you got to pay them to install it. So say it's $250 and it costs them, I don't know, $250 to install. It's $500. To save $20-30 on a sensor, I think I would stick with the calibration free ones. I'm not sure we can get one that still requires calibration anymore. I'm sure somebody makes one, but I'm not aware of it. I didn't really look either though, Andy. What else? Anybody else? Doug's very impressed with my telestrator skills. Kicked John Madden's ass, apparently. Well, this is a modern-day telestrator. It's really easy to use. Anybody else? All right. If you do have questions, you see my email and my phone number on there. So just send me a note or call my cell phone there, and I'll do my best to answer questions as they come up. And then hopefully some of the gas utilities in Illinois have some very exciting news to tell us in a couple months about their CO2 rebates changing. So I'll let them save their thunder for that. Thank you guys for calling in, and I appreciate it. We'll talk to you.